Here we are. Back to AP Stats. It is Thursday, October 22nd, 2020. We're going to be doing the introduction to section 2.2 about density curves and normal distributions. Okay. So we're going to begin kind of formally defining what a normal distribution is so that now we can use it. So first, what is a density curve? Here's the definition straight from the textbook. A density curve is a curve that is always on or above the horizontal axis and has area exactly 1 underneath it. Right, a density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Right, so when they say it has an area of 1, it's because when we add up all the proportions, right, a proportion would be a percentage that's a decimal. Right, when we add up all the proportions, it adds up to 1. In other words, it's 100% of the data is represented under that curve. Right, in statistics and probability, we say, essentially you always have a proportion that has to range from 0 to 1. Right? So everything added up is 1. Density curves, like distributions, come in many shapes. A density curve is often a good description of the overall pattern of a distribution. Outliers are not described by the curve. Right? So our density curves don't really exhibit the outliers. No set of data is exactly described by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. So the density curve may not yield the same proportion as using the actual values, but it is close enough that we can use it. And it provides a good enough approximation. The reason we like to use density curves is because we can more easily find information about them, and there's resources to help calculations be much easier. All right, density curves. All right, so if you're writing these down for your notes, would you mind raising your hand so that we know you need more time if you do? Correct. Looks like we're good. All right, so here's some examples of density curve, right? We have this history on all 3 pictures. So the ITBS vocabulary score distribution. Right. In this figure here, the histogram of the Iowa test of basic skills, ITBS, vocabulary scores of all 7th grade students in Gary, Indiana. Right. The smooth curve shows the overall shape of the distribution. Right. So this red curve that goes up and over our distribution shows the overall shape. Notice that it is not completely above the entire distribution, that it cuts off some of the histogram bars and is above some of the other ones. Right? And that's because we're essentially where the curve is drawn is we're trying to cut bars and leave space above bars so that if we take all those cuttings, we can fill in all the gaps very closely, so to say. And that's how we get that really close approximation of the 1 under the curve. Right, so if we look at figure A on these other 2 graphs, right? We're looking at the proportion of scores less than or equal to 6.0 on the actual data. That's this one on the left. So notice how the bars are all shaded in here. If we use the actual data, we get a proportion of 0.303, or 30.3% if we're thinking of it as percentage. So if we use our actual data, we get this proportion, 0.03. The proportion of scores less than or equal to 6.0 from the density curve is 0.293. Okay, so we're 0.01 off, right? But that's not a ton of difference, right? It's just a tiny bit. And we can see we're only shading now under the curve. Now to calculate this, like if I was saying, hey, calculate the actual area under the curve based on this specific example with this specific curve, you would need you'd need calculus and an understanding of calculus to do that. We're not going to do that. You will not be expected to show your work on how to calculate the area of the density under the curve. We cannot do that. That's not going to be expected. There are tables of values that we use to do this. All right, and that's how this was determined. It uses a table that tells us, hey, if we're at this point along our density curve, there's this proportion of data that is under the curve to the left of that point. Typically, we use to the left like a percentile. It's all the proportion below that number. That's kind of how density curves will work. All right. Is there anything I can clarify here? I know it's kind of a weird set of information. Okay. And if you are taking notes or drawing these pictures or writing anything down, can you raise your hand if you need more time? Okay. All right, next slide. All right, describing a density curve. Right, we can describe a density curve very similarly to how we just describe a regular distribution. All right, so measures of center and spread apply to density curves as well as actual sets of observations. Right, so how we would describe the center and spread of a density curve is essentially the same as we would describe a center and spread of a distribution. Areas under a density curve represent proportions of the total number of observations. The median of a density curve is the equal areas point. Right? The point with half the area under the curve is to its left, and the remaining half of the area is to its right. So where our median is, left of the median, 50% to the right of the median, about another 50%, half and half, cut down the middle. The mean of a density curve is the balance point, just like in a distribution. The point at which the curve would balance if made of solid material. Okay, so the median is the equal areas point. The mean is the balance point. The mean and median are the same for a symmetric density curve. Apply at the center of the curve. And the mean of a skewed curve is pulled away from the median in the direction of the long tail. And this is a lot of what we've seen in describing distributions. Right? In a symmetric distribution, the mean and median should be about the same. In a skewed distribution, the mean is pulled away from the median in the direction of the tail. Right? Can you raise your hand if you are writing this down and need more time? Okie dokie. Is there anything I can clarify? All right. Here's some pictures to make it a little more illustrative. So we have two curves. We have a symmetric curve, right, where the mean and median are in the same place, right there in the middle. It's our balance and the half. In the other one, we have a skewed distribution, skewed to the right. The median is the cutting it in half point, right? 50% of the data is over here, 50% is over here. The mean is our balance point, and it is pulled in the direction of the skew. Again, this follows what we've already been talking about, what we've talked about previously about distributions. Would anyone like another moment to draw the pictures or write anything down from this screen? Okie dokie. Another little figure description here. This is kind of a visual on the balance point, right? If I were to have a curve and it's made out of like metal, like the whole thing is just solid metal. If I try to balance here, it's going to topple over to the left. If I try to balance too far to the left here, it's going to fall over. But right here, it's just right. The weight is equally distributed. Right? So we have that. It's another illustration of the balance point idea. This brings us to normal distributions. Right? Previously, I have told some of you, or told you guys in class, that we should not be calling anything approximately normal yet, because we do not have the criteria to do so. We can say something is roughly symmetric or approximately symmetric, or that it is symmetric, but we cannot call something normal. Normal distributions, or something that's approximately normal, has to fit certain criteria. And we're going to get into that criteria now. And normal distributions are kind of based on this idea of normal curves. All right, one particularly important class of density curves are called normal curves. The distributions they describe are called normal distributions. All normal curves have the same overall shape. They are symmetric, single-peaked or unimodal, and bell-shaped, which means they have that peak and then they taper off on both sides, right? So you could have something that is symmetric and unimodal, but it only tapers on one side. That would not be normal in the sense of how they're using this as a specialized type of curve and distribution. Any specific normal curve is completely described by giving its mean, mu, right, mean of the population, and its standard deviation, sigma. And that's what these two symbols are. It's mu, the Greek letter mu, and the Greek letter sigma. Right? And that is standard deviation of a population. So if we look at these two curves, we have this kind of like more spread out short curve. So remember, on the density curve, the area under the curve has to be 1. So if I have a more spread out curve, it's going to be shorter. If I have a less spread out curve, right, a smaller standard deviation, it's going to be taller. Right? I can't have a really tall and really wide curve. Then the area would add up too much. And then we have, so again, a description of this. Two normal curves showing the mean mu and standard deviation sigma. Right? And so this bar here is 1 standard deviation greater than the mean. And in this one, even though it's a smaller width, this is also 1 standard deviation away from the mean. Anyone need a moment to write anything down from this screen? Please raise your hand. Pause here. Right. Looks like we're good. All right. Last thing here, we have the mean is located at the center of the symmetric curve and is the same as the median. So again, in both of these pictures, the mean and median are both the same value. They're both the value of mu. Changing mu without changing sigma moves the normal curve along the horizontal axis without changing its spread. And this is similar to what we saw earlier this week with adding or subtracting a constant. Right? If I add or subtract a constant, just a number, to a distribution, and I do that to all the numbers, it will shift the distribution. Right? So the location of the mean and the median and the quartiles and all that move. However, our measures of spread do not change, and the shape does not change. Right? So the graph just shifts up or down the x-axis, depending on information. The deviation sigma controls the spread of a normal curve. Curves with larger standard deviations are more spread out. Right? So there's more variability in a curve that has a larger standard deviation and less variability in a curve that has a smaller standard deviation. Right? But knowing the median and standard deviation allows us to essentially draw the picture of the graph. Right? And we'll get into that next week, which I had intended on doing today, but again, things happen, and yeah, we're not getting that far into the content today. So, can you please raise your hand if you need another moment to write anything down from this screen? Okay. Is there anything I can clarify about what we've seen so far, right, with our normal distribution or with the density curves? All right. So last thing I want to do, we are done with the lesson part. I just want to go and look at one thing in Canvas with you guys. This. That worked. Okay. And we're going to go here. That's super tiny. All right. So in our week 9 CYU here, I had anticipated getting a little farther into the content on today's lesson than I actually am. So the last question on this is essentially going to be a bonus question. It's going to be kind of like extra credit. So I've rearranged the point values for the other 3 questions that you should be able to answer. And then this last question having to do with normal distribution and density curve. You can try it. It will essentially earn you extra points. It has a value of 0 points. So if you do it, you'll get you'll get points for it. So it can offset getting another one wrong, or it could earn you extra credit on this assignment essentially if you attempt it. So you can try this one if you like. You might need to, if you want to try this one, you're going to have to look a few pages farther into the book than where we ended today. And you can see the page value, the page numbers for today's lesson is in the class resources for today. and that'll give you the range of where this information is on how to draw one of these. Okay, so I wanted to go over that with you guys. I couldn't delete the question when I realized that this morning because some people had already attempted the quiz, and that messes things up if I deleted the question. So I just had to change its point value. And again, there is a discussion board for today as well, that you should be able to